Digital signatures are crucial in ensuring the authenticity and integrity of digital information. This simple yet powerful technology has revolutionized the way we authenticate digital content. Let's delve a bit deeper into how digital signatures work and how they have become so integral in our increasingly digital world. Digital signatures, at their core, are the digital equivalent of a stamped, sealed, and signed document. They are a mathematical scheme for verifying the authenticity of a digital document or message. The underlying technology behind digital signatures is public key cryptography, a revolutionary cryptographic system that uses a pair of keys for encryption and decryption. Each digital signature has a unique pair of keys, a public key that everyone can see and a private key that only the owner knows. When a document is digitally signed, the signing software creates a hash of the document, encrypts it using the owner's private key, and attaches it to the document. The recipient, upon receiving the document, uses the sender's public key to decrypt the hash. If it matches the hash they generate from the received document, the signature is verified. In addition to verifying the sender's identity, digital signatures also ensure the integrity of the message. If even a single character in the message changes after the signature is attached, the hash changes and the signature becomes invalid. This guarantees that the content you receive is exactly what the sender intended. This intricate dance of codes and keys is what makes digital signatures such a robust tool in today's digital landscape. They play a pivotal role in verifying the identity of the sender and ensuring the integrity of the message. Digital signatures authenticate the sender by proving the origin of the message and ensuring it hasn't been tampered with. These complex yet effective tools offer a multitude of benefits within the digital world. Essentially, digital signatures serve as a digital fingerprint of the sender. They are generated using certain algorithms that encode the user's information into a unique format, a process that adds an extra layer of security in digital communications. Their role in our increasingly digital society is becoming more and more critical. They are being used to verify the identity of a person or entity involved in a digital transaction or communication, thus ensuring the integrity of the transaction and protecting all involved parties. They offer a secure way to validate authenticity and prevent fraudulent acts. Take, for example, software distribution. One of the critical areas where digital signatures are used is in the release and distribution of software products. Developers use digital signatures to sign their software, providing assurance to the user that the software they are downloading is indeed from a trusted source and has not been maliciously altered by a third party. In financial transactions too, digital signatures play a crucial role. By adding a digital signature to a transaction, the involved parties can not only verify each other's identity, but also ensure the non-repudiation of the transaction, which means a party cannot deny their involvement in the transaction. In a nutshell, the application of digital signatures is vast and critical in our digital age. They help us to navigate the digital space with an increased level of trust and security. Digital signatures are essential for authentication in secure communications, software distribution, and financial transactions. Certificate authorities, often referred to as CAs, hold a significant role in a world that urgently requires digital security. They are the trusted entities that issue digital certificates, a critical tool in the vast landscape of digital security. These certificates are not mere electronic papers. They are the embodiment of trust, of reliability in the digital sphere. Designed to authenticate the holder, these digital certificates are akin to digital passports or IDs. They are used to verify the identities of entities, whether individuals, machines, or organizations, thus facilitating secure communication in an increasingly digital environment. But how is all this possible? How are these certificates managed? The answer lies in the system known as Public Key Infrastructure, or PKI. It is an intricate network of policies, procedures, hardware, and software expertly designed to create, manage, distribute, use, store, and revoke digital certificates. The PKI system does far more than just manage digital certificates, though. It also handles key pairs, which are essentially pairs of encryption and decryption keys, crucial for ensuring the confidentiality of communication. Furthermore, the PKI system manages the overall security infrastructure. It oversees secure transactions, protects identities, and maintains the integrity of data across networks. In conclusion, the role of certificate authorities and public key infrastructure cannot be overstated in our increasingly digital world. Public key infrastructure manages digital certificates, key pairs, and the overall security infrastructure. Creating a digital signature involves steps using asymmetric cryptography. This process, while technical, is the cornerstone of modern digital communication and security. Asymmetric cryptography, or public key cryptography, is an essential method used in securing internet communication and protecting sensitive data. The process begins with creating a pair of keys, a public key and a private key. The public key is known to everyone, while the private key is kept secret by the user. When a document is digitally signed, the signature is created using the private key. This signature can be verified using the public key, thus ensuring the authenticity of the sender. Verification is a crucial stage in the process. Without it, the digital signature would hold no weight. This act of verification ensures the signature was created using the private key that corresponds to the public key of the sender. This prevents any tampering or forgery, which are significant concerns in the world of digital communication. Moreover, verifying digital signatures provides a level of assurance about the integrity of the message. It ensures that the message was not altered in transit. If the message had been changed after the signature was applied, the verification would fail. This is how the system provides a failsafe against illicit alterations to documents or messages. In conclusion, the creation and verification of digital signatures are fundamental to maintaining the reliability of digital communications. They provide a sense of trust, a critical attribute in this digital age. Verifying digital signatures ensures the authenticity and integrity of the message. ECX 509 without a doubt is the standard format for digital certificates. This is a worldwide recognized format that provides a benchmark for authenticity and reliability in the digital realm. Of course, any discussion about X509 would remain incomplete without mentioning its key components that define its structure. These components act as the backbone of this format and provide the necessary information for the certificate to function effectively. The first component is identity information. This includes the name of the entity or the person the certificate is issued to. It's like a digital ID card that helps to authenticate the person's identity in the digital world. This identity information can include, among other things, the name, location, and the organization to which the person belongs. Next comes the public key. It's a long string of data that's generated uniquely for each certificate. This public key is used for encryption and decryption processes, ensuring the data you send and receive remains secure and unaltered. Then we have the digital signature. This is generated by the certificate authority and is unique to each certificate. The digital signature helps in verifying the authenticity of the digital certificate, ensuring that it has not been tampered with. Another vital component is the validity period. This refers to the time frame for which the digital certificate can be used. After this period, the certificate becomes invalid and a new one needs to be issued. And last but not the least are the certificate extensions. This is an optional component and can contain additional information about the certificate. The additional information can include restrictions on the use of the certificate or extra details about the user or issuer. To sum it up, X509 is the standard format for digital certificates. The robust structure provided by its key components, identity information, public key, Digital signature, validity period, and certificate extensions ensures the reliability and security of digital interactions. A practical demonstration of creating and verifying digital signatures will be provided. Students will engage in hands-on exercises to reinforce their understanding. Potential challenges in digital signatures include key management, quantum computing threats, and evolving security standards. Future developments include post-quantum cryptography and blockchain-based signatures. The importance of digital signatures and certificates in securing digital communication will be summarized. Understanding digital signatures in cryptographic protocols is emphasized.